too many of these chapter 27 homework problems, so I'll just talk about these a little bit here. This cube has a negative charge. The minimum field that could exist is 5 units inward. Why? Because I've got 20, 35 pointing in and 40 pointing out, so I need at least 5 more pointing in, so I have a net flux pointing in. So that's how I'd solve that. Draw cross sections through which the flux is 2q over epsilon sub 0, q, 0, and then 5. So I did these in different colors. It's a little weird. Over 0, surrounding the negative 2 and positive 2q, over plus 5, surrounding the plus 2 and plus 3, over plus 1, surrounding the plus 2 and negative 2. And then just plus 2 is around something like that. So for problem 28, the net electric flux is only dependent on the enclosed charge. So that's plus q. So therefore the flux is plus q over E sub 0 if I surround this whole thing. I know this kind of looks like an avocado, which is weird, but it's a positive charge with a hole surrounded by a neutral conductor. So the neutral conductor isn't relevant to this problem if we think about the flux of the whole thing. If we're thinking about field strength and flux in different regions in here, that's a little bit different. But surrounding the whole thing, it's just that. For problem 36, this is given as the formula. So basically that means if it's positive and it's r hat, it's directed radially outward. So that tells me it's probably a spherical type shape. So at 0.2 meter radius, we've got 200 newtons per coulomb. Here, so it said the diameter of 0.4, that's annoying. So actually the radius is 0.2. So I had to fix that down here. Initially I got an area 4 times bigger than it was supposed to be. So that's annoying, just that, I don't know, that's annoying. So to get the surface area is 0.503 square meters, 4/3 pi, or 4 pi r squared is the surface area of a sphere. So in this case then, to get the flux, charge over vacuum permittivity, Q divided by E sub 0 would be this. So if I want to find the charge enclosed, it's flux multiplied by E sub 0. So again, the flux here is going to be the field strength times the area. So this comes into play. I can figure out the flux with this. That lets me figure out the charge. So that's 8.9 times 10 to the negative 10th coulombs. That's actually 0.89 nanocoulombs. The book had said, the answer in the back of the book was off by a factor of 100. Okay, so for problem 37 here, we've got a plus 100 nanocoulomb charge, hollow area here, and then this one here is going to have a, let's see here. I think it was a negative 150 nanocoulomb charge. I have to look at that. Darn it. Hold on, let me grab the book. Did these last week. Okay, so, so then the neutral conductor has a hollow cavity, so then negative 50 nanocoulomb is transferred to this. So this whole thing has a negative 50 nanocoulomb net charge. So the inside of this would be negative 100. The outside would be positive 50. The charge on the outer surface, therefore, is going to be plus 50. So basically what that means is if I have something like this, I have a shape like this, and I move this over, make it a little bit bigger here like so. At this point, when I'm enclosing both this charge and the inside of the conductor, the net field, the field in here has to be 0 in the middle of this conductor because the net charge enclosed is 0. So there is no flux through this red ring that I've drawn right here. Get rid of that. So down here, problem 45, what's being asked is, says find the electric field inside and outside a hollow plastic ball of radius r that has a charge q uniformly distributed on its outer surface. So that's acting like a conductor, even though it's not, because the charge is all on the outer surface. So I don't know why they said that. So just inside, the electric field is 0 newtons per coulomb, so no charge is enclosed, and the field is always 0 inside a conductor. And here, since it's uniformly spread out, it's acting like a conductor. So in this particular case then for part B, just outside, we look at that radius r, figure out the charge enclosed. So this is the formula basically relating it to electric flux. Divide area, and we get the charge divided by the surface area and vacuum permittivity. So you could do kq over r squared is equal to the electric field strength, which is something we've kind of known already, or q over 4 pi epsilon sub naught r squared. Those mean the same thing. 46, I want you to think about this. So essentially, there are 4 regions to this where you're trying to figure out the electric field strength. Uniformly charged sphere here of radius a, if it's uniformly charged, that means it's a plastic ball. That means it's a non-conductor. And that's actually really hard to figure things out. So I think that's going to be tough. In this region here, between radius a and radius b, negative q is the charge enclosed, so that's going to be easy to figure out, the electric field in here. In this region, between radius b and radius c, you're within a conductor, so there's going to be no net charge enclosed and no electric field. When you're greater than c, you're enclosing the plus 2q here, the negative q here, so you have a net charge enclosed of plus q. That's going to be easy to figure out as well. So these are my thoughts of how to figure this out. So I'm going to the next page, and you can see that B, C, and the last 3 are quite easy to figure out. So the charge enclosed here is negative q. That's the electric field strength. Charge enclosed here is 0, since there'd be positive q on the inside surface of the conductor. The net charge enclosed would be 0. And for greater than C, the total net charge enclosed is plus q, so that would be the electric field strength, or you could say that directed outward. Here you could say this is directed inward instead of a negative. Okay, for this part it's really hard. So the first thing I've got to do is figure out the charge density in coulombs per cubic meter. So I know the volume, any particular of the whole entire inner plastic sphere is A, is the radius of that. So the volume is 4/3 pi a cubed. So since the charge that's available is negative q and it's evenly distributed throughout that, this is the charge density. Now, that's the charge density, so it's charge per unit volume here, but for anywhere where r is less than a, we're not going to enclose all that charge. So not all of negative q is going to be enclosed, something less than that will be. So when I look at this, this is again my formula for flux. E times A is equal to Q, the charge enclosed over vacuum permittivity. So for any radius, the volume that's enclosed is 4/3 pi r squared. Now, if r is the full radius of A, then you would enclose the full amount of charge, which is negative Q. But if r is less than A, you're going to enclose less than that amount of charge. So the charge enclosed is density times volume. Coulombs per cubic meter times cubic meters will give me coulombs. So that's the charge density that I figured out up here. This is the volume for any radius r over here. Notice the 4/3 pi's cancel out. So I get negative q r cubed over a cubed. So that tells me the charge that's enclosed for any radius. To find the electric field strength now, when I use this formula and move down below, I get that E times this area for, again, any radius, R, is equal to the charge enclosed divided by this constant. So essentially, I can say E is equal to the charge enclosed divided by 4 pi r squared times that constant. And that's what I've got down here. So this charge enclosed is something I figured out earlier. That's this. This is the surface area. Oh, and by the way, the charge enclosed is negative q r cubed over a cubed. So it's kind of, should have drawn a line around that, I guess. And this is the area of 4 pi r squared. So notice r cubed and r squared partially cancel out. So I get that as my electric field strength, or you could say that directed inward. So that's tough, right? So the key thing is you've got to find out the charge density, multiply that by the charge density by the volume of whatever sphere you have of radius r. That will tell you the charge that's enclosed, and then you apply that to the electric flux formula. So I'm going to see if I can, maybe I can do this. This here is the charge that's enclosed. So if I look at this, that goes from there to there. So that's how I get that. So charge enclosed divided by the area and so forth. Okay, so I think that's it. Hopefully that makes sense.